Check.
All right, and
Check.
hello everybody. I'm Ethan Siegel, and today we're going to be talking about the 3 ways the James Webb Space Telescope is going to revolutionize the universe. But we're going to do this for the lowbrow astronomers. So what I need from you is I need an introduction and a confirmation that we've got the whole room set up for everyone. So let me pass it over to you guys.
All right. Okay, thank you, Ethan. So can you hear me okay?
Yeah, you sound great.
Okay, got it.
Okay. Got stadium echo.
Yeah.
Makes it more exciting.
We might have to just deal with it. I'll try to talk low, so maybe I'll minimize it. But I'd like to welcome back once again to us Ethan Siegel, who is an astrophysicist, blogger, podcaster, and a communicator of science to the public. He also currently writes for the NASA Space Place column, which many of us, I understand, read regularly. Ethan did his undergraduate studies at Northwestern University and then went on to earn his PhD in physics from the University of Florida. This was followed by a master's degree in education under his thesis advisor, Dr. Pamela Gay, who actually we did a remote connect and did a meeting with her a few years ago, if you might remember. And of course, we have the prestigious honor of having him speak to us again. I think this is your third time, is it not, Ethan?
I think it might be my third. I think I've spoken to you twice before about 2 pretty different topics, and James Webb Space Telescope's a brand new one for all of us. So very excited to talk about that.
And also maybe Ethan will mention something about his latest book before he is done here too. So with that, I'm going to turn over to Ethan Siegel.
All right. Well, thanks very much. The way this is going to work is I'm going to tell you guys all about the James Webb Space Telescope. As Jim said, I do have a new book out. So for those of you who have not picked up Treknology, the science of Star Trek from tricorders to warp drive, if you're a science fan and a Star Trek fan, this is an incredible overlap that I got to do between all the different technologies and scientific advances that Star Trek had sort of envisioned, and to go through the real life science of where we are as far as achieving those. As you can see, I've got plenty of copies, so if anyone from the club wants a signed copy, just let me know either after the talk or through one of the lowbrow officers after the talk, and I'll get it signed and shipped off to you so we can figure that out. I'm going to talk for probably about 40 to 45 minutes, and then we'll have a great Q&A time to work with that. So we'll go as long as we need to, and things will be as exciting or, as you want to make them. So we're going to go through this, and no questions are going to be off limits. So without further ado, let's get started talking about the 3 ways that the James Webb Space Telescope is going to revolutionize the universe. So when it comes to, saying 3 ways, I want to just come right out and say what these 3 super revolutionary things are going to be. When the James Webb Space Telescope launches, probably in about a year and a half, because things have been delayed a little bit. And that's okay. It's way more important with an expensive flagship mission like this to get it right the first time, right? When we launched the most famous flagship mission in NASA's history, when we launched the Hubble Space Telescope, what was it that happened? Well, we launched it in 1990, and as soon as it saw first light and took that first image, we recognized, oh no, there's something wrong with the optics there. Now, there was a lot of debate over what do we do and how do we deal with this. For years, we took data with the flawed instrument, with the flawed mirror, and we just attempted to process it on the ground as best as possible. It was a very bold decision when we decided that we were going to launch the space shuttle to dock with the Hubble Space Telescope and service it. Since we've done that, we've serviced it a number of times, and it's become, without a doubt, the most famous telescope in the world, even though it's out of this world orbiting it. It's become, in a lot of ways, the most revolutionary, as far as our picture and conception of the universe goes, observatory we've ever had. With James Webb, we're not going to have that option. What we're going to do with James Webb, instead of launching it into low Earth orbit, it's very important that James Webb be as shielded as possible from any sort of heat, light, or radiation. So we're sending it to the L2 Lagrange point. This is a point, if you take the Earth and the Sun, right? So Earth and the Sun, and you're saying, okay, L2 is on the other side of the Earth. It's about 1.5 million kilometers farther away from the Earth than low Earth orbit is. 1.5 million kilometers is about 4 times the maximum distance that the moon reaches from the Earth. This is going even beyond where Earth's shadow cone comes to an end, right? The sun shines on Earth and it makes a little cone of shadow, where eventually, because the disk of the sun is bigger than the disk of the Earth, it's going to converge and you won't have a shadow anymore. The L2 Lagrange point lies beyond that. That's where James Webb is headed. The farthest any human's ever gone from Earth is about 400,000 kilometers. And that was during Apollo 13, where they reached and went around the far side of the moon and came back. So we're talking about 4 times as distant from that. There are no plans to service it. James Webb was not made serviceable. So it's way more important to get it right here on the ground to alleviate any potential pitfalls before we launch it. Because once it's there to stay. And any flaws that we launch it with, it's going to have for its entire lifetime. So I, like almost everyone, would rather they take the time and the care to get it right than potentially open themselves up to a situation where we have a flawed observatory in space. So what's James Webb going to do? Well, James Webb, in a nutshell, is going to teach us how the universe grew up. If the Hubble Space Telescope taught us what the universe looks like, which it did in spectacular fashion, in the mid-1990s, the most famous proposal that was ever put forth said, I want to take the Hubble Space Telescope and I want to point it at a patch of nothing in the sky. I want to point it at a region of sky where there are no stars, no galaxies, no nebulae, no light sources of any types. Out of the plane of the galaxy, out of the ecliptic of the solar system, towards a tiny, minuscule region where we really don't know of anything bright or notable. They pointed the Hubble Space Telescope at that region of sky, and they waited and waited and waited and waited. They took image after image after image after image and just stacked them on top of one another. For over a week, they imaged the same nothingness in the sky. This was an extremely brave move by the director of the Hubble Space Telescope to greenlight this proposal, because the big risk is, hey, we've got the most powerful, most exciting observatory ever, and we're just going to kill time. We're just going to waste time on this. That was the big fear. Well, what they took wound up being called the Hubble Deep Field, and imaging this tiny region of a sky for days and days and days. When you finally added up all those individual photons that were collected and you said, what is it that we're looking at? The answer was thousands of galaxies suddenly appeared in the depths of space. This was the deepest astronomical image ever taken at the time. And since then, Hubble has done even better because we've upgraded its instruments. It can now see from the ultraviolet into the infrared. And this is extremely important. It's extremely important to see into the infrared because light, you'll have to remember, is defined by its wavelength. The wavelength of any photon is what determines its energy. And your telescope, you want it to be as big as possible because the number of wavelengths that can go across your telescope mirror determines what the resolution of your telescope is. So if you want to look to longer wavelengths, you're going to have lower resolution with the same size telescope than shorter wavelengths. But the big bonus to going to longer wavelengths is you can see part of the spectrum you wouldn't see otherwise. In an expanding universe, this is a really big deal. An expanding universe like our own, where you said, okay, I'm going to start at the Big Bang, and the universe expands and expands and expands and expands. Well, what happens to the light that you generate in an expanding universe? If you generate some light in space, and the light has a wavelength that's a certain size, right? That's your wavelength of light. As space expands, then the distance between any 2 points stretches, which means the wavelength of your light stretches. And it goes to longer and longer and longer wavelengths as time goes on. And at longer and longer and longer wavelengths, that means your light looks redder. That's where we get the term redshift from. This is a cosmological redshift, where your light, whatever it starts off at with a wavelength, it gets stretched to larger wavelengths, which means redder wavelengths. It's enough that if you look at the most distant galaxies that the Hubble Space Telescope sees, they emitted ultraviolet light. And the expansion of the universe since this ultraviolet light was emitted has been so significant and so severe that it went from ultraviolet into the visible part of the spectrum, from violet to blue, all the way down to red, and then into the infrared portion of the spectrum. That's how significantly this light has been stretched by the expansion of the universe. And in the best deep field image we've ever taken, this is now known as the Hubble Extreme Deep Field. With the most advanced cameras that they have on Hubble, they took data for a total of 23 days in a number of different wavelength bands, predominantly in the infrared, all the way out to Hubble's maximum wavelength of 1.6 microns. That's 150% longer than the longest wavelength of light that human eyes can see, than the reddest reds we can perceive. Pretty good. In a region of space that was 1/32 millionth of the entire sky, the Hubble Space Telescope managed to reveal 5,500 galaxies. If you were to just take that extrapolation, you would find that there are approximately 200 million galaxies. Sorry, 200 billion galaxies. That's 5,500 times 32 million and round up. There would be about 200 billion galaxies in our observable universe today. Now, thanks to what we know about how structure forms in the universe, we think these are only the biggest, brightest galaxies that we're able to see. We estimate that most of the galaxies that are out there are smaller, lower in mass, less luminous, and therefore still invisible to Hubble. Some of them are at such great redshifts, at such great distances, that they come from when the universe was early, young, and very, very small. Even the shortest wavelength light that could have been emitted, by time it arrives at us today, it's too long for Hubble's eyes to detect. So going deeper into the infrared with a bigger, more powerful telescope is what's going to make James Webb so exciting. And the three big advances that it's going to give us are, first off, because we can see farther into the universe than Hubble or any observatory allows us to see, and with better resolution, James Webb Space Telescope is going to teach us how and when the first stars and galaxies formed. We have some indirect evidence for when the first stars and galaxies formed. We have our simulations based on what we know is in the universe, and they indicate that you might get stars when the universe is maybe 1 or 200 million years old, and you might get galaxies at 3 or 400 million years. But there's a lot of wiggle room there. And I say there's a lot of wiggle room because we don't know, hey, this is what an average fluctuation looks like, an average overdense region in the early universe. That might grow into stars and galaxies, and that's just fine. But what happens to a non-average region? What happens when you have a large fluctuation or a very small fluctuation in the opposite direction that gives up its matter to the regions around it? Can you get stars and galaxies forming even earlier? What does the distribution of this look like? The James Webb Space Telescope, instead of going out to 1.6 microns, which is Hubble's limit, and instead of having a telescope that's 2.4 meters in diameter, that's the size of Hubble. And the reason that's the size of Hubble is that was the largest mirror that they could fit inside the space shuttle that launched it. Well, the James Webb Space Telescope is going to be significantly larger than that. It's going to be 6.5 meters in diameter instead of Hubble's 2.4. And because area works as radius squared instead of just radius, this is going to translate into about 7 times the light gathering power of Hubble. And yet it managed to do this. James Webb is going to do this despite launching in a smaller rocket than the space shuttle that took Hubble up. How does it do that? It has segmented folding mirrors. So if you've seen that hexagon honeycomb shape of the James Webb Space Telescope, it was designed like that so it can fold up and fit inside a European Space Agency rocket and launch while all still being contained inside. This is a tremendously brilliant design. It's going to unfold in 2 stages and then have an extendable tower that's going to come down for a secondary mirror. All of this, though, needs to fit inside that rocket it's going to be launched from, and that's why it's segmented. So you unfold it, and instead of going to 1.6 microns in wavelength, it can go all the way out to 30 microns. That's 20 times as long a wavelength as Hubble can see. Yes, at longer wavelengths, you get fewer wavelengths that can go across the same distance, but they built the telescope bigger, and also they have the capabilities to go cover that whole spectrum. So the shortest wavelength James Webb Space Telescope can see is about 550 nanometers, or about half a micron. That's pretty good. That comes into the visible range. It means we're going to be able to see reds and oranges and maybe yellows for colors in the visible part of the spectrum. But James Webb is optimized to go way into the infrared, so it can see these long stretched wavelengths that Hubble will never be able to see. It's going to be able, if we combine this with gravitational lensing. And let me tell you about that for a second. When you look out at the universe, you're seeing, okay, I'm looking in a direction and I'm going to gather all of the photons that come in. If there were some way to magnify these distant galaxies, you'd be able to see more of the light coming from them because you could magnify them. Well, space comes pre-equipped with natural magnifiers. Why? Because just like in optics, if I had a lens that focused light, you'd say, oh yeah, I get more light. That's why if I take a magnifying glass and hold it out in the sun, I could accidentally set like a blade of grass on fire or something. Well, in space, we don't have optical lenses. We have gravitational lenses. This is a brilliant prediction that goes all the way back to Einstein. Einstein's theory of general relativity predicts that we should have these gravitational lenses. The way it works is if you're observing over here and you have a mass here, a real big mass like a quasar or a galaxy cluster, big mass, what happens is this mass is going to curve the fabric of space so that any light that comes from behind it is going to get bent due to the presence of this mass. So mass acts like a gravitational lens, which means it stretches, distorts, but magnifies and enhances the amount of light coming from behind it. Gravitational lensing was discovered observationally back in the 70s, despite being predicted by Einstein some 60 years beforehand. Since we've discovered it, we've used it to great effect. And finally, we're starting to quantify it, to understand it. And we know where we see these galaxy clusters. If we point James Webb at specific locations around these galaxy clusters, that's where it should be able to look the most deeply into the universe. The things that it can see perhaps 10 or 12 or 20 times faster, with that much less observing time than the things that we're just, looking at in regular space without this magnifier. So we should be able to look back, even if you emit this ultraviolet light, even if you emit this shortest wavelength light a star can emit, the expansion of space will stretch it, but the gravitational lensing effect will magnify it, and it should arrive at the James Webb Space Telescope capable of being seen. So that's the first huge thing that James Webb is going to do. Now, those of you who are pretty astute are going to tell me, hang on, I know there's got to be a problem with that. And there is. You're going to say, the problem is, if I were to just launch a telescope and put it out into space, the sun's going to be shining on it. And a shining sun, even if we put it far away from Earth, is going to heat that telescope up. Those of you who have night vision goggles, right, or those of you who've done infrared astronomy, but those of you who've looked through anything with infrared eyes know that it sees heat. And it can only see things that are warmer than its ambient surroundings. So for the James Webb Space Telescope, if it wants to observe this long wavelength, 30 micron light, what it needs to be able to do is cool itself way down, is to cool its instruments way down so that it can actually go and observe these things without getting swamped by thermal noise. If you had your night vision goggles and you point it at a fire, you're not going to see anything because the fire is so hot, it's just going to saturate everything. James Webb has to worry about this, both for the near infrared and the far infrared. If you've seen pictures of Hubble, it looks like it's covered in aluminum foil, and that's to reflect all the sunlight away and keep it as cool as possible. It doesn't do a very good job. If we equipped Hubble with the same instruments on James Webb, it would be super saturated. It wouldn't see any of that. 1.6 microns is about the limit of Hubble. How does James Webb go out to 30? There's two methods that it uses. One is a brand new technology called the sun shield. This is passive cooling, right? What it does is it has these 5 parallel layers of, basically, it looks like plastic, but it's enormous. And what it does is, if the sun is over here and the James Webb Space Telescope is over here, this shield that comes in 5 layers is going to face the sun. So the entirety of the James Webb spacecraft faces away from the sun, and you have this big shield that stands between the telescope and the sun. On the sun-facing side, that outer layer is going to heat up to temperatures of about 360 degrees. It's going to be very hot on the sun-facing side. But this passive cooling has been engineered so that each successive layer gets cooler and cooler and cooler. And it doesn't require any coolant of any type. It's just going to let things cool down passively. Heat will flow out of the sides, heat will be reflected away and radiate away from these various shields. And the spacecraft on the far side of this should be kept cool. In fact, it should reach temperatures that are below 70 Kelvin, which is to say it's cold enough that nitrogen would be liquid. All through passive cooling, we don't need any active component. That'll get you the near infrared stuff. That'll get you way farther than Hubble can go, maybe out to 5 or even approaching 10 microns. But if you want to get out to 30, you want to see those first stars, you need active cooling on top of it. And that's what the mid-infrared instrument known as MIRI is going to be doing on the James Webb Space Telescope. It comes with its own self-contained coolant. And so James Webb, it's going to deploy all its different systems, and then we have the mid-infrared instrument is going to be actively cooled with, I believe, a pump that's going to allow us to adjust how cold does it need to be kept and when. So that's the key, is you cool everything down and you cool it below the noise floor you need to actually make these observations. The light comes in, and then you know, here are these galaxies, here are these stars that are more distant than anything we've ever seen before. There's one more obstacle to overcome if you want to do that. There's the problem that let's start by telling you the story of how you form stars and galaxies, right? So we have the Big Bang, everything expands and cools. You fuse together your light elements through nuclear fusion. As long as the universe is hot and dense enough, things expand and cool more, and you can stably form neutral atoms. That takes about 380,000 years. And then you have to wait. You have to be extremely patient, because the most overdense region that the universe was born with is less than 0.01% denser than the average density. Gravity will pull things in over time, but it takes a large amount of time to build that up, right? It takes time to allow gravitational attraction to clump matter together. That clumping is going to take a really long time. It takes, and this is what we argue about, is it 50 million years, 75 million years, 100 million years, 150, 180, 200? Before the very first star forms, before this gas collapses and contracts enough and reaches cold enough temperatures, or reaches rather the right conditions to ignite nuclear fusion in its core? This is what the James Webb Space Telescope is going to find out. But there's another problem. The problem is, even when you form your first stars, what's going to happen? Your star forms in an environment where it is surrounded by this neutral matter. So what you need to have happen is you need to form enough stars that you can ionize these neutral atoms, and then the starlight can stream towards you. So James Webb has to fight not only the expansion of the universe and not only the thermal properties of its own environment, but it has to fight these neutral atoms from tens of billions of light years away. It needs to fight these neutral atoms from before the universe was full of stars. We do know how long it takes all of the atoms to become reionized. This is something that Hubble has studied. It's called reionization, and it takes about 550 million years. But large pockets of the universe get reionized partially or majority-wise well before that. So that's the big hope that James Webb Space Telescope is going to do for seeing the first stars and galaxies. But by measuring how much light gets absorbed, how much light gets transmitted at all these various locations and various epochs in time, James Webb is going to teach us a second thing that is vitally important to understanding how the universe grows up. That second thing it's going to teach us is where all of the universe's star-forming gas actually goes. So when you're looking out at the universe and you're seeing, oh, we see some stars here and we see a galaxy here and we see an older galaxy here and we see a brighter galaxy here, you don't just see that light. That light, yes, as it travels towards you, it's going to get stretched by the expansion of the universe, but it's also going to pass through all of the intervening matter between where that light gets created and where the James Webb Space Telescope is to observe it. So if we have neutral atoms here, it's going to get those absorption features, and it's going to tell us how much of the universe is ionized versus how much is neutral, and where, as we look farther and farther back. So as we find more distant objects, we're going to see, oh, the universe was this much ionized here and this much ionized here. When you do have a large burst of star formation, how much of a reprieve, how much of an ionized bubble does it create before you run into neutral atoms again? So the second big thing that the James Webb Space Telescope is going to teach us is where does all of the universe's star-forming gas actually go? So just by looking at the distant universe, two of the greatest puzzles that we still don't know the answer to today, when do the first stars and galaxies form and what do they look like? James Webb will get that. James Webb will also get, hey, all this material that we need to form stars and galaxies and that populates intergalactic space. Where does it go? What happens to it? And when does it get ionized again so that the universe becomes transparent to visible light? That's another question that the James Webb Space Telescope should answer. It's a little more sophisticated, but it's just as important to understanding how our universe evolves and grows up. There's an old saying in astronomy that one astronomer's noise is another astronomer's data. And most of the people who work on star or galaxy formation don't also work on intergalactic medium astrophysics. But these two camps both need the James Webb Space Telescope. And the more you learn about one, the more it teaches you about the other. This is sort of a fascinating interplay. But James Webb isn't just designed for looking in the distant universe. You've seen a whole slew of things that Hubble has brought us back. It's looked at objects in the solar system. It's looked at nearby stars and star-forming regions. It's found the pillars of creation in the Eagle Nebula. It's taken infrared views of many of these different star-forming regions and supernova remnants, as well as the big extragalactic and cosmological work that Hubble's done. Well, James Webb is no different. And there is a third milestone that it is prepared to tackle that we have not seen tackled really by anything else. And that is in the field of exoplanet studies. Now, Hubble's lousy for exoplanet studies. It's done direct imaging of a few different large exoplanets in orbit around young stars. It's seen brown dwarfs. It's seen super gas giants that are separated far enough from their parent star. And that's pretty much it. That's kind of the limit of what Hubble can see. Our best planet-finding spacecraft, those of you who've been following it probably know it's Kepler. What Kepler did was it took a look at a large portion of sky towards the galactic plane into one of the spiral arms close to us. Kepler Space Telescope took a look at that, imaged about 150,000 stars over a continuous period of about 3 years. And every star that has planets orbiting it in the same plane as our line of sight, which is to say, when we look out at it, these planets, they can go around any way they want, which is to say they're random. The planets can go around like this, they could go around like that. But if relative to our line of sight, these planets cross in front of the star, then when they pass in front of that star, they're going to block a tiny fraction of the star's light. And using this technique, Kepler has discovered thousands of stars with planets around them, including stars with not just one discovered planet, but with up to 8. We have stars that we found with up to 8 planets. And in one of the most famous ones, using a slightly different telescope, we very recently discovered 7 roughly Earth-sized planets around a single star just 40 light years away. This is the TRAPPIST-1 system, and this is as far as we're concerned, this is the probably the closest system we know of with so many Earth-sized planets around it. It's absolutely fantastic. So with that said, we want to know, for these Earth-sized planets, particularly the Earth-sized planets that may be in the habitable zones around their star, where they have the right temperatures for liquid water on their surface if they have Earth-like atmospheres, we want to know, do they have any signs of life? This is a huge challenge for astronomy. It's something that everyone is going to be racing to do. The 30-meter class telescopes that they're building, such as the Giant Magellan Telescope, or the European Extremely Large Telescope, or the 30-meter telescope that may or may not get built on Hawaii, those 3 observatories are all scheduled to come online in the 2020s, and the Giant Magellan Telescope and the European Extremely Large Telescope are on track to do it. We're looking at mid-2020s for a fully operational 30-meter class ground-based telescope. They might be able to see whether there are characteristic signatures of life in the atmospheres of these planets, but James Webb should get there first. And the way James Webb is going to do it is, when these planets pass in front of their parent star, they not only block a portion of the light coming from the star, so we can see a dip in the light curve and then a rise again as they pass off the star. What we expect to see while this occurs is that when we look at the atmosphere of a planet that passes in front of its star, most of that light where the solid stuff is gets blocked, but sunlight's going to filter through the atmosphere that surrounds the planet. When you're off of the Earth and you see a sunset, you're seeing a ring of sunset everywhere on Earth. This is why during a total lunar eclipse, the moon turns red. It's not that something's happened to the sunlight that's hitting the moon. It's that that light is blocked by the shadow of the Earth. But there's all those sunsets and sunrises in a ring around Earth's atmosphere, and that red light can still fall on the surface of the moon and get reflected back to us. That's why the moon turns red during an eclipse. Well, if we set up a good enough observatory on the moon, we would be able to break that sunlight up into its individual wavelengths, and we'd be able to see what type of elements, atoms, and molecules are present in Earth's atmosphere. This is the whole science of spectroscopy. And spectroscopy doesn't give us these fascinating pictures like we get from the Hubble Space Telescope using photometry. James Webb, with its infrared imager, with its near-infrared imager, the mid-infrared and the near-infrared imagers, it's going to return spectacular pictures. But what it's also going to do is, it's also got, separately from photometry, it has the ability to do spectroscopic astronomy, which means for the large enough planets that, are large relative to the star they orbit, if they're close enough, it should be able to tell us what are the atmospheric contents of these worlds. And this is fascinating because, we know some of the stuff that's out there. We expect we'll find water. We expect we'll find, hydro things, ammonia, methane, water, compounds that are hydrogen heavy. But we also expect, if we get lucky, we might start seeing some molecules that seem a little bit familiar. We might start seeing carbon dioxide. We might start seeing nitrogen. We might start seeing acids. We might start seeing inert gases, like here on Earth, about 1% of our atmosphere is argon, the noble gas. But the biggest signature that everyone would just be super excited for is if we found an oxygen-rich atmosphere. Here on Earth, 21% of our atmosphere by mass is oxygen. There is no world that we know of that has even 1% oxygen in its atmosphere. There may be some inorganic, some non-life driven ways to make an atmosphere that's rich in oxygen. But we haven't really conceived of a way to do it that would get you up past more than a handful of percent. If we see something where an atmosphere is like 10, 20, 30% oxygen, we are going to lose our minds. We're going to lose it because we're going to be so excited that we have found what I would call a smoking gun for life on a world beyond Earth. That's one of the three main ways we're looking for life in the universe, is through these exoplanet studies. The other two are, one is way more ambitious, like SETI, looking for active aliens or extraterrestrials that are intelligent and spacefaring and communicative. And the other way is much more mundane. It's looking for like tiny microscopic evidence for fossilized life on a world in our solar system like Mars. Maybe one of those two other methods will pay off. But if we find this, if we can find signs of life or no signs of life around the nearest Earth-like candidate planets to us, James Webb Space Telescope is likely going to be the observatory to do it. So to recap, right, James Webb is going to be open to the public. It's going to be a revolutionary observatory when it launches. It's also arguably the most complicated observatory humanity has ever designed and built to go explore the universe. It's going to be launched 1.5 million kilometers away from Earth to the L2 Lagrange point. It's going to deploy in flight and have an enormous sun shield, brand new technology for James Webb, that's going to deploy and passively cool the spacecraft down to below liquid nitrogen temperatures. Once that's done, when it wants to do infrared observing in the mid-infrared at its longest wavelengths, it's going to cool down that infrared instrument, that mid-infrared instrument, and going to get it down to about, I believe about 6 or 7 Kelvin, just 6 or 7 degrees above absolute zero. That's cold enough that none of the thermal noise will impact the photons that are coming in. So as long as the sun shield stays intact and the cooling works properly, and the mirrors are undamaged and reflecting the way they should reflect infrared light, which is, by the way, why they're gold. The gold-coated mirrors on the beryllium substrate, that's designed to optimally reflect not visible light, but infrared light. So that's why the mirrors are the gold that they are. And this is all part of, designed to solve the problems it's built to solve. It wants to. James Webb scientists who built it, designed it, worked with it, they want to answer these questions. They want to see farther into the universe than we've ever seen before. They want to know, do we have the evidence for stars and galaxies back at a time before we've ever seen stars and galaxies so far? One of the people who was instrumental in doing some of the best science with Hubble, Garth Illingsworth, at last year's American Astronomical Society meeting, said that James Webb will teach us more about the first stars and galaxies in one day than all of astronomy's observatories combined have taught us about it up until this point. And that's a fascinating statement. So for the first stars and galaxies, nothing is going to compete with James Webb. For where did that first star-forming gas in the universe go? When did it become ionized? How is it distributed? James Webb will do what nothing else has ever done in giving us that answer. And finally, on a very different scale, here in our own galaxy, James Webb is going to be able to observe these very nearby planets around low mass stars, and it's going to tell us their atmospheric contents. We won't be able to see an Earth-sized world around a sun-like star, but around the smaller stars, the M dwarf stars, the red dwarf stars, we should be able to measure the atmospheric contents of Earth-sized worlds if they're close enough. And we already have a handful of candidates. TESS, the transiting exoplanet something something, is the observatory. That's what the two S's are for, I'm sure of it. That's going to observe and seek out these candidates. It's going to look at nearby stars to say, what should be the great targets for the James Webb Space Telescope? That's what TESS is. TESS is optimized. It's very similar to the Kepler spacecraft in terms of what it's outfitted with. It's a lot less expensive than Kepler, but its mission is going to be more similar to the K2 mission, where it's going to look for these Earth-sized planets around nearby stars that may potentially have the right conditions for liquid water. And it's going to identify those as the most optimal candidate planets for the James Webb Space Telescope to look at. So with that, how the first stars and galaxies formed, where the universe's star-forming gas went, and what signs of life do the nearest Earth-like candidate planets have, the James Webb Space Telescope is going to begin its life answering 3 burning questions in astronomy that nothing else has been able to answer. And with that, I think this is a great time to say thank you and to open it up to the audience for questions. So thanks, everyone.
So we have an answer to that. Transiting exoplanet survey satellite.
Survey satellite, transiting exoplanet survey satellite.
I prefer something myself.
Question, well, 2 parts actually. Do we know whether or not before the beginning of the reionization period, if the universe temperature was cold enough for molecular hydrogen to form, and if so, would that make it easier for the Webb telescope to spot the more ancient matter out there?
Okay, I'm going to ask the person closest to the microphone if they can repeat that question for me, because I heard something about neutral hydrogen, but that's pretty much all I got.
Okay.
That's why I moved this out.
Okay. Do we know if it was cold enough before the reionization period for molecular hydrogen to form? And if so, would that make it easier for the Webb telescope to examine the early part of the universe?
Okay, that's a really good question. So the question is, in the early stages of the universe, do we know if it was cold enough for molecular hydrogen to form rather than atomic hydrogen? And the answer is this depends much more on density than it depends on temperature. So where you have matter clumped together, you should start to see some molecular hydrogen. The vast majority of it is going to be atomic hydrogen, but there should be some molecular hydrogen in these nebulous regions around where stars and galaxies, or proto-galaxies collect. But predominantly, this is going to be atomic hydrogen, not due to anything with temperatures, which are absolutely cold enough to form diatomic molecules, but much more with densities. Because even though we talk about gravitation clumping different parts of the universe together, what we're actually experiencing is these molecules, these atoms are having a hard time finding each other. Today, the average density of the universe is about 1 proton per cubic meter. Well, if you go back to when the first stars were forming, the universe was way more dense. We're talking maybe 10,000 times as dense as it is today. But 10,000 hydrogen atoms per cubic meter is still not very good odds for forming diatomic hydrogen. You really want a much larger density. So it's really only in the regions around stars and galaxies in these dense nebular regions, or where you have a cloud that we start calling them molecular clouds instead of like the atomic intergalactic medium. So James Webb should encounter that. There should be, hydrogen molecules in some of these regions. And theoretically, if the density of this H2 is high enough, it should be able to see it spectroscopically. But that's a very tall order. That's a very tall order for the telescope.
Thank you.
Questions? Go ahead, Jim.
You talked about TRAPPIST-1 as with the 10 Earth-like planets.
Can you repeat that, Jim, if you're up close?
I'll get closer.
Okay.
TRAPPIST-1 with all the Earth-like planets.
Yes.
It is a brown or red dwarf.
TRAPPIST-1 is a red dwarf. It is low in mass. It's about the physical size of Jupiter, and it's burning at a temperature of about 3,000 Kelvin. So it's about half the temperature of our sun. What happens around TRAPPIST-1 is we know of at least 7 roughly Earth-sized planets around TRAPPIST-1. The innermost 3 are very likely too hot to have life on them. They're more like Venus or Mercury style temperatures. The outer one is too cold, right? Even though these things are orbiting pretty quickly, they're all way interior to like Mercury or Venus's orbit. But they're so, the star is so cool and so low in luminosity that it's really these intermediate planets, the 4th, 5th, and 6th ones, that are the most interesting for potential life. These planets should be tidally locked to their star, which means they orbit with the same face, always facing their star, just like the moon always orbits Earth with the same face facing us. But what should happen is it will have a hot side, the side that always faces the sun, which should be pretty roasted. And it should have a cold side where it's just all frozen because it never gets direct sunlight on the far side. So some people, I like this name, call these eyeball planets because it has a frozen side where it's got like a blue color from the frozen ices we imagine. It's got like a roasted side, and then it has this ring around it where the sunlight just sort of glances at it. This is where we think the ideal location for life ought to be. So being able to not only probe the atmosphere, but to probe the atmosphere around the ring-like portion where we expect is the most likely candidate for life should be the ideal way to look for life on these worlds. TRAPPIST-1 as a red dwarf star, about the size of Jupiter, means that when an Earth-like planet, Earth-sized planet passes in front of it, it's blocking a significant fraction of the star's light, maybe up to like 1% of the star's light, which is huge. If you were to take Earth and pass Earth in front of the sun The sun has 109 times the diameter of the Earth, which means the Earth blocks less than 0.01% of the sun's light. So these planets that are passing in front of TRAPPIST-1 are like 100 times more effective at blocking starlight than Earth is for the sun.
My question about TRAPPIST-1 is this star old enough to have oxygen form on these planets? As I understand, it took a long time to have oxygen, enough oxygen in our atmosphere to support anything except anaerobic microbes.
That's a really good question, right? So this really low luminosity star, and it's got like, maybe it's less than 10% the mass of the sun. It's 40 light years away. It's really low luminosity. It's got like 0.005% the brightness of our sun. But age is a huge question. How old is this star? It's actually older than the sun. We estimate, based on the properties of the parent star itself, the star TRAPPIST-1, it appears to be about 7.6 billion years old. So it's definitely had enough time, if life got started there and has sustained, that absolutely it should have oxygen. The biggest question about TRAPPIST-1 that pessimists have, and there are good reasons to be pessimistic, is can a star that's as low mass as TRAPPIST-1, that has the level of flares and activities that a red dwarf star has, can a planet orbiting it still hang on to its atmosphere? Or will all of these words be like Mercury or the moon with no atmosphere at all? Well, James Webb should be able to answer that, because if there's no atmosphere, we'll figure that out pretty fast. But if there is an atmosphere, then the conditions are probably good enough that if we got lucky, then just maybe there should be oxygen there too.
Other questions?
Right. Someone online has asked me the question about James Webb being launched to L2 and asked if there wouldn't be a better point to launch it to, right? When you launch something, right, here's the sun, here's the Earth, and here's L2. L2 is on the far side of the Earth, 1.5 million kilometers away. That's still close enough that you can transmit data from James Webb to Earth without too much trouble. That's pretty good for communicating, right? If you want to send a signal to the James Webb Space Telescope, it takes you about 5 light seconds for a one-way trip. You could say, well, what if the problem with L2 is it's unstable, right? When James Webb runs out of fuel to keep it thrusting in orbit around L2, it'll slowly drift away. That's an unstable point. Well, there are 2 Lagrange points that are stable, L4 and L5. These points make an equilateral triangle with Earth in orbit around the sun. If you put a spacecraft at L4 or L5, however, you run into this difficulty of now to communicate with Earth, you've got, instead of like 5 seconds of a one-way light travel time, you've got about 6 minutes of light travel time. You've got a much longer amount of time that it takes to go ahead and communicate with your spacecraft. So that's actually the thing about it's probably more like 10 minutes one way. That's kind of a big reason not to launch James Webb to one of those points. We want it to be close enough that we can communicate with it, but far enough away that it's not getting any of the effects of Earth or Earth's atmosphere to provide drag on it. All right. Do we have a question from you, lowbrow astronomers in the room?
Excuse me if it's a stupid question, but I Googled James Webb Telescope, and the primary mirror and the secondary mirror is not covered. like a a normal Gibsonian or Newtonian.
That's right.
So I was wondering, um, will that affect such sensitive telescope, like the ambient light from planets or Earth or the moon or whatever? Would that ambient light affect the telescope? That's question one.
That is not a stupid question at all. And so thank you for asking it. If we did not have this sun shield on it, this would be a tremendously important problem, right? Because there is all of this ambient light from everywhere that's going to strike this. So if you had reflected light from Earth, or you had reflected light from the moon, or you had emitted light from the sun, and it impacted the optics of your telescope, even from behind on the secondary mirror, this could be a disaster, because that amount of light could not only cause interference with what you're trying to collect, could not only cause pollution in your data, but it could potentially fry the optics in your telescope. There has been a long-standing campaign from planetary scientists to get the Hubble Space Telescope to point at the planet Mercury. People want to image the planet Mercury with Hubble. It would make it the greatest pictures of Mercury ever taken by a spacecraft that wasn't named Mariner 10 or Messenger, which are the only two spacecraft to have visited Mercury. And they won't do it. In the late 1990s, I had the opportunity to speak with the people who made those proposals. And they said that every year they made the same proposal. Every observing cycle, they made the same proposal. They said to the people who allocate time on Hubble, we want to look at Mercury, here's why. And every time they get the same thing back, which is, this is an extremely good mission. The science merits are tremendous. It is an excellent proposal. We have no recommendations to change it. And also, as long as I am in charge of allocating time on this telescope, we will never observe Mercury. And the reason is, it is too close to the sun. They did not want to risk pointing anywhere near the sun, because if you get the tiniest bit of sunlight on your optics directly, they're sensitive enough that they're going to be fried. The tolerance of the James Webb Space Telescope, which is to say how thoroughly aligned each individual mirror and between mirrors is in order to focus the light, needs to be about 20 nanometers. Direct hit from a sun-based photon can destroy that. So it can warp your mirrors, it can cause optical problems, just direct sunlight. Therefore, you have this sun shield. And remember, we're on the far side of the Earth. So you have the sun, the Earth, the moon goes around it, and then way over here is James Webb. And this sun shield will block all of the light. It will block the moon's light, the Earth's light, and the sun's light, so that all you have is the outer solar system. And now you're dealing with things that are far enough away, things like Mars, Jupiter, Saturn, the galaxy, that these are not going to interfere with you. The only thing you really have to be responsible enough to do is to not point the optics of James Webb at one of these planets when you're trying to observe something behind them. That's the danger of light pollution, that you'll get something that strikes your primary mirror and reflects onto your secondary, and now you're designed to look at something that's like plus 28 magnitude, because you want to look at, say, an ultra distant galaxy, and instead you're looking at something that's like -1 magnitude because you're looking at Mars. So don't do that. But as long as you avoid that problem, any of this other ambient light, because of the shape of the James Webb mirrors, it's going to get reflected away to a point where it won't impact the secondary and it won't mess up your image. So we're safe from all the interior worlds, and all the exterior worlds are far enough away that as long as we don't point at them when we're not trying to observe them, we're going to be protected from their light pollution.
The second question is, for a big telescope like that, won't you have the chance of getting hit by asteroid or shooting star? And what's the backup or solution for to prevent that?
Okay. So this is a good question. The question is, when we have a telescope like this, right, it's pretty big, it's in space, it's going to get hit by space debris because we live in the ecliptic plane. The James Webb Space Telescope is going to live in the ecliptic plane, and this is full of stuff. Asteroids, comets, and little bits of micrometeoroids, these little dust particles that poke holes in everything. The odds of getting hit by a comet or an asteroid are astronomically small, but if it happens, it will be the most momentous event of bad luck we probably ever had on a space mission. But that said, these micrometeoroids, the space dust, this stuff moves fast. On average, space dust moves at a speed of like tens of thousands of miles or kilometers per hour. This is stuff, because kinetic energy is 1/2 mv squared, that big V, even for a tiny m, means that V squared gives this a lot of kinetic energy. Absolutely, we expect that some of this is going to smack into mirrors over time. And when that happens, yep, like we're going to have mirror degradation. That is just something where, well, now on this part of the telescope, light doesn't get focused properly. So we do expect some mild degradation over time. Hopefully it will be small. We expect it will be small. We have other satellites that have been up at L2 before and for long periods of time. And over the time scale that James Webb should exist, the optics should be okay. On the other hand, the sun shield has a very large cross-sectional area. The sun shield is very, very big compared to the optics on the James Webb Space Telescope, and that will undoubtedly get hit by these micrometeorites, or meteoroids, because they won't be on Earth, they'll be in the James Webb's netting. So when they built these sun shields, they built them with a segmented, vented design with periodic rip stops all through them. We know that over time, there are going to be holes poked in these shields, maybe even holes in many of the shields. But the way we've designed it should mean that these holes don't line up. So when you get a hole in one, there isn't a hole in the same spot where sunlight could pass through in the next one. The odds of having that exact angle be punctured is extremely low. So we don't think that's going to happen. We also have a large number of rip stops, so that this is like designed to avoid the Titanic problem, right? When the Titanic hits an iceberg, the inside of the Titanic fills with water and it goes down. The way they solve that is they put in different sections. So you puncture a part of a big ship and that section might fill with water. But there are so many other sections that aren't filled with water that it stays afloat. That's kind of like what they did with the James Webb Space Telescope sun shield, that each one of these 5 layers has a set of ripstops. So if a big meteorite comes through and causes a little tear, and that tear starts to run, it's going to stop. It's going to stop after just a few centimeters. So there are all of these ripstops in there, and by putting them in, they should keep that degradation to a minimum. It should happen only extremely slowly. The consequences of having puncture, of having a degraded sun shield means that what would happen if that were the case is that temperature that the sun shield would cool you by would start to rise. So instead of being like 60 Kelvin, you might be talking about like 80 Kelvin or 90 or 100. And when that happens, you start to lose your window, both in mid-infrared and near-infrared, for how far out you could actually see. So it's really those extra, the longest wavelengths, the farthest distances that you start to lose. But you should still be extremely good at anything except the extremes of what James Webb was designed to probe. So that means, maybe unfortunately, it means you want to do your most ambitious, most distant observations in the earliest stages of having an operational James Webb Space Telescope. But that was a tough question. It's a good thing that every year I go and talk to the people at Northrop Grumman at the American Astronomical Society meeting who are building this thing, because I would not have known that 2 years ago.
Hi, I have a question about the solar shield. You have the solar wind pushing on that. Is that going to cause problems pushing it, maybe being uncontrollable?
So that's a good question. The question is, when you have these big, like, shields, the solar wind's going to hit them, and that could potentially create a torque or a net push from a flux. How is that going to change the James Webb Space Telescope? And the answer is, hopefully not significantly, and we don't think it will be, for two reasons. One is that James Webb Space Telescope is pretty massive. It's almost as massive as the Hubble Space Telescope. So inertia-wise, it's pretty hard to push something that heavy just with a sail, right? The reason that solar sails have this reputation for spinning out of control is because they're so low in mass. But the second thing is that James Webb is going to have its own onboard fuel for steering and for orienting itself and for even course correcting to keep it in stable orbit around the L2 Lagrange point. So the solar wind at its maximum could potentially exert a very small force. But as long as the James Webb Space Telescope corrects for that with its onboard thrusters, that shouldn't be prohibitive for anything until the day comes where it runs out of fuel. When that day arrives, when it runs out of fuel, then it's going to start having some real problems. But like many things, it's been over-engineered so that even though it's being launched for a nominal 5-year mission, we can fully expect that if, and there's a big if, but if it launches and launch goes off without a hitch and deployment goes off without a hitch, we can easily get a decade or more of quality observations out of JWST.
Any other questions?
Whoa, we're getting a question from someone with a better beard than mine. I like this.
So
Sorry.
you said that any question is fair game. So the first one is, what brand of mustache wax do you use?
Okay, first question about mustache wax. Why not? I use a mix of 3 different types of mustache wax. I used to have a solo mustache, and it kind of wanted to separate because I grow it up here by my nose and I grow it down here on the outer parts of my lip, and it wanted to split. And one day I just ran with it and said, what if we try to make my mustache and my mustache's mustache? And it worked great, and so I've kept it ever since. I use 3 brands. One is, the softest wax I use is Oregon Wild Hair Wax, which is a very soft wax. I use Firehouse Tacky Wax, which gives me more of a hold. And then I use a homemade, very firm wax, and I mix all 3 of them together and put them in. And that's what allows me to get the style I want with the hold that I need, because I have very coarse hair, and just the softer waxes on their own won't do it. If I had softer hair or finer hair for my beard and mustache, I'd be able to get away with using the softer waxes, but I need that extra hold.
I guess you add some optical pitch then to that homemade wax. But anyway, on to a serious question. I would assume that they want to keep the sun shield pointed between the optics and the sun. So the optics themselves are independently steerable. Can you cover basically an entire hemisphere
Right. So this is a good point, right? The thing is, because of how you have to orient the sun shield, wherever your sun is, right, there the Earth is, and then here's your sun shield, and you need the optics on the opposite side, which means you get a 180-degree view at any given time. So you can't look everywhere all at once. You can only look in the away from the sun direction at all times. So if you're saying, oh, there's some great stuff happening over there, well, you can observe it as soon as the Earth orbits around the sun enough to allow you to observe it. This means if there's an important transient event that occurs, you don't have 100% chance that James Webb is going to be able to see it while the event is going on, because it can only see at any given time half of the sky safely. Now, they can try and cheat that if they want, to say like, okay, like the sun's over here and what we want to observe is over like there. And we're facing this way. So maybe we can turn it like that so we're still with our back to the sun, but they're probably not going to do that, not until, you know, a lot of data has been collected, because any risky thing that you do, people are probably going to be very conservative about not doing. There is so much good science to do with James Webb. People are so excited about proposing for it that they expect this will break all of Hubble's records as soon as the first observing cycle is open to the scientific community, because it is a public observatory. That, you know, we have a few priority missions that are going to be part of the observing campaigns, but then the rest of it, you can apply for it. That's been true with all of NASA's space telescopes, and it will be true with James Webb. But if, for example, we detect another neutron star merger or black hole merger, and all of Earth's telescopes go to look at it, James Webb might not be able to. If it happens in the wrong part of the sky, sometimes you get bad luck, but sometimes you get good luck. So 50% of the time, we expect to be able to see whatever good thing happens wherever it happens.
Thanks.
All right.
Any other questions? Okay, I think we're finally done, Ethan.
All right. Well, thanks everybody. Thanks for a great Q&A. Thanks for being a great audience. And as a reminder to everyone, if you haven't got your copy yet, I'll be more than happy to do one, because this is good stuff.
And Ethan, before we let you go, I'm kind of looking funny here because I'm leaning on a table so I can mute our speakers and then talk to you at the same time.
Great.
But we would like to give you a gift for your appearance for us. I think last time we sent you, I believe, a T-shirt or sweatshirt.
You did send me a T-shirt. I do wear it. I do wear it sometimes, although I needed the long sleeve version today.
Well, do we have some long sleeves, Doug? Anyway. Okay. So we thought of one option. We do, I believe, have a hooded sweatshirt. A couple of other options. We thought we could make you an honorary member and also put you on down for the Astronomical League through us, but then you might resent the email hit. Or another option is we could send you a gift certificate for wherever you like to eat.
Oh, that's really sweet. Well, I'll tell you what, I'm always in need of more long sleeve shirts out where I am. So with or without a hood, I would absolutely love that, and I would proudly wear it. I would happily be a proud shirt wearing member of the Lowbrow Astronomers from University of Michigan.
And the size on that?
Probably a large.
I think we heard that as a large.
All right.
Okay, with that, Ethan, we're going to give you a big round of applause and thanks again.
All right. Thank you, everybody. And now the whole internet knows my shirt size. All right. Have a great night, everyone.